All right, so chapter 9, lesson 1, identities and proofs. So we're going to be doing stuff similar to what we've looked at before. We're going to look at them graphically and see if they could or could not be an identity. And then we're actually going to prove identities. So one of the things to remind you that an identity is an equation that's true for all values of x and wherever it's defined. And sometimes you're going to need to use different identities to solve different problems or to solve different proofs. And we've looked at a lot of identities back in chapter 6. At the end of chapter 6, we had that whole list of identities that we worked with, and we're going to be using them again. Okay. Just a reminder about the testing them graphically, that it's important that you go through, and almost any of them that we're going to do, we're going to prove them if you can. Okay? And so the first thing you might want to do is check them out graphically and see if they work. And then go ahead and do the proof then if you can show graphically they work. So, all right, so we're going to go ahead and do this exploration here to see what happens with our graph. So let's go ahead and make a viewing window in our calculator from negative pi to pi for x and negative 2 to 2 for y. And then we want to graph both sides of this equation. Okay? So we want to graph cosine of x in y1 and this other side in y2. Okay? So first use that window and check to see if it's could be an identity. And you should be in, hopefully, you should be in radians here. So. Okay, so when you graph them, they look alike, right? But it's hard to tell because, so we need to do something to make it look like it. So if I go ahead and graph them, here's a graph of cosine, and here's a graph of the other one. And we can see that by following the path, that those do appear to be an identity if we look at it from that viewing window. So let's go ahead and say, so they do appear to be the same, identical, but now let's change our viewing window to go from negative 2 pi to 2 pi and see what happens to it. So where our sine function continues to show the sine wave, this other function. Now remember, what's the degree of this other function we have? What's the degree of it? 8. The degree is 8. And what do you know about, and not only is it 8, but it's positive, right? Because it's positive x to the 8th over 40,320, which tells me that the end behavior of this graph is going to smile. So eventually, there's no way it could match that graph. Okay? But from negative pi to pi, it does. But if we look at it with a bigger window, then it obviously doesn't. So sometimes the windows don't always tell us a story, and the graph doesn't always tell us a story, so we have to be able to prove them. So whenever I look at a graph then and say that, okay, could that be an identity, then we're just going to say it possibly could be an identity, but we're not going to say for sure that it is could possibly be one. Okay? All right. So let's go ahead and look at these first two. For number 1 here, it says, is either of the following equations an identity. And so here we're just going to, and this is something we've done already, so it's nothing new, all right? But let's go ahead and graph them and see if you get an identity for them. Okay, so if we graph these two, and I'm going to go ahead and change this so it follows the path. So if I graph them, here's my first one, and I probably should have changed that window a little bit, right? But we can see that obviously, looking at this, even from that standpoint, that these are definitely not, right? So let me stop it. And hit zoom 7. Here we go. So there's the graph of the left side of our equation. And here comes the graph of the right side, and they're definitely not the same. Okay, so those definitely could not be an identity. Okay. So how about the other one then? How do I put cotangent in? Like more tangent. All right, so we check this one. And here's the graph of the left side. And this is going to have asymptotes wherever sine is 0, right? And here comes the right side. And we can see that they do follow the same path, so this one, they would be an identity. So I would say that it could be an identity then. Oops, that's not what I was supposed to have gotten. Okay, so then we're going to look at, all right, so here I've got the equation, or the expression 2 sine of x cosine of x, and they want us to graph this function and see if we can find an identity for it, or what could be an identity for it. So take 2 sine of x cosine of x, and put that in your y equals, and see if you can tell what would be an identity for that. So what does that graph look like? Does it look like cosine or does it look like sine? Does it go through the origin or is it at a max on the y-axis? Okay, this goes through the origin, right? So that means it would be sine, right? So what kind of sine would it be? What's the amplitude for this graph? Goes up to what? Up to 1 and down to -1, right? And here's our 1, here's -1. Okay, up to 1 and down to -1. Okay, how many times does it repeat itself in 2 pi? How many times does it repeat itself in 2 pi? If we just start at 0 and go to 2 pi. It repeats itself how many times? 2 times, right? Okay. So if it repeats itself twice, what does that tell you? What's the period then? The period is pi. So then that tells me that the value of b is 2. All right, hold on, let me get back here. I'm struggling there now. All right, here we go. There we go. So this would be what would it be? So the amplitude is 1, and so then it would be sine of what? 2x. Okay. Sine of 2x, because sine repeats itself twice. Right? So our value of b is 2 because this has a period then of pi. So see if you can determine. Okay, so if we graph this, cosine squared minus sine squared, we get this graph here. And what would be the function there then? Okay, f of x equals cosine of 2x. It has from 0 to 2 pi, it repeats itself twice. So that tells me that the period is going to be pi, so then you would have the cosine of 2x. Okay. Right. And these are actually going to be identities that we're going to use eventually as we're going through this. All right. Now, proven identities. So useful feature of trigonometric functions, they can be written in many different ways. So one form may be easier to use in one situation. Different form of the same function may be more useful in another. So back in lesson 6.5, we looked at all of the different identities. And so here's a look at those basic trig identities one more time. So we've got all of them here. We've got the quotient identities, that tangent equals sine over cosine and cotangent equals cosine over sine. We've got all of our reciprocal identities here. We'll be using them. The periodicity identities, those we won't be using nearly as often. Maybe once in a while we might use them. But the main ones we'll be using are the quotient identities, reciprocal, the Pythagorean identities. Remember, you should have those written down somewhere as 9 different versions, okay, 3 for each. And then the negative angle identities we'll be using. So we'll be using all of those identities to be able to prove. Now, if we look at the graphs of identities, we can say, okay, yes, maybe they're true, maybe they're not true, but at least we have a good idea. Graphically, we can say definitely not, but graphically we can't say for sure. Okay, we would have to prove it. So we're going to look at some strategies then for proving that trig identities. So we can use algebra and previously proven identities to transform one side of the equation into the other. Okay? And quite often we're going to want to, if they're to the first degree, we're going to want to make sure we get everything into sine and cosine. Right? That's the easiest way to do them with their first degree. Number two, if possible, write the entire equation in terms of one trigonometric function. So if we change everything to sine or everything to cosine, and here it says that too, express everything in terms of sine and cosine for number three. Now the thing is when you have things that are squared, then we're going to want to use identities there. Deal separately with each side of the equation. It's very important that you do this, that focus on one side, simplify it to as best as you can, and then go to the other side and work on that one. And sometimes once you get to the first side done, then it kind of makes sense what happens with the other side. And then this one we're going to use rarely, but we might use this a little bit. If we can prove that AD equals BC, in other words, if we've cross-multiplied, okay, if we can prove AD equals BC, then we can conclude that this proportion is also an identity then. Okay? So we're going to be using those rules along with those identities. So if you don't have those identities out, you're going to want to locate them. Now, one of the things is there's often a variety of ways to proceed. And the thing is, it takes lots of practice to do this. And that's why we're going to be doing a lot of these in the next few days. And so you have to be patient with this. And if you start going one direction and it doesn't seem to be working, okay, then start another. Now, one of the things is that don't erase everything. Okay, here's a situation where we're not going to erase. All right? If I start on a path and it's not going very well and I'm not getting anywhere and I decide to go a different direction, don't erase it. Just cross it off and then keep working, because you don't want to lose the previous work, because if you go back and if you need to start again, you don't want to go back to that other situation. So here's a situation where you're going to be crossing stuff out, not just erasing it. Okay? It's important to learn the relationships among the trig functions and to simplify an expression by using the equivalent one. Now, here's one of the mistakes that was made on the test the other day, is that these are not equations, okay? These are identities that we're proving. That means I can't move things from one side to the other. Okay? I can do things to both sides, okay? Right? But I can't move things. So if I had a plus sine of x on one side of the equation, I can't subtract sine of x from both sides to get rid of it. Okay? Right? It's not an equation. You're proving that the two sides are equal, and so we can't move things each way. Right. Here's a reminder of some of the Pythagorean identities and things we'll do with them. But here, this note here, it's a good idea to check graphically. If it appears they're the same, then prove it. Okay. All right, so let's do number 3 here. Now, this one we already did, right? This was in our previous example that we did. And so graphically we said, okay, these do look the same, so now we're going to prove that they are. So we want to use identities where we can to simplify. So let's just focus on the left-hand side first of all. On the left-hand side, we've got 1 plus cosine of x minus cosine squared of x over sine of x. Now, look at this. Do you see any identities? And the thing you're always going to look at is there anything that is squared? Okay. Whenever I have anything squared, I want to look to see if there's an identity there that I can use. So here I have a negative cosine squared. Is there an identity up here that we can use for that, to simplify that? Right. Chris, do you see one? Could I use the one that's, use this one here? Okay. I could do that, all right? But notice that also, and that's the thing is that there's going to be different ways. You might see something that John doesn't see, and John may see something else, okay? All right. So Chris sees that. So we can go ahead, and that's one approach we can take. So let's go ahead and do that. So 1 plus cosine of x minus 1 minus sine squared of x. We just replace cosine squared with 1 minus sine squared. Okay. Now, wait before you write, okay? I want you to just watch me do this, okay? And then you may decide, because we're going to do this two ways now, all right? Because maybe somebody else saw something else. Okay? So we have 1 plus oops, need my denominator. And this is over sine of x. I'll give you a chance to write this down. So we have 1 plus cosine of x minus 1 plus sine squared of x over sine of x. Okay, we're just focusing on this left side here. Okay, so what happens now then? Can I simplify anything? What's that? It won't cancel out yet. Okay, can't cancel out yet. Okay, what else do I have? Okay, I have a positive one and a negative one, right? Okay, so we have cosine of x plus sine squared of x over sine of x. And we're still looking at, we have sine of x plus cotangent of x on the other side. Bring that down here. Well, that would just put us right back up here. Oh, cosine over sine is cotangent? Okay. So that means, so what can I do here with this left side then? So let me write that. John said that we could have, this is cosine of x over sine of x. Okay? So can I take this left side and make it look like that right side, or can I take the right side and make it look like the left side? Either way, it doesn't matter. The whole goal is to see, can we make the two sides equal to each other? Now I look at this and I have this sine of x in the denominator is a common denominator, right? Which means I can do what? What's that? No, I can't. Okay, you can't do things on both sides. All right, you can't get rid of this. It's got to stay here. Okay? But this is the common denominator, correct? That means that not only can I write it as a single fraction, I could write it as two separate fractions. So if I wrote it as two separate fractions, now I have something I can simplify, right? Cosine over sine is cotangent. And sine squared over sine is that the same as what we started with here? Okay. That's the same thing, isn't it? Because adding is commutative. So here I have just, so now it is done because I have both sides equal to each other. Okay. That's one approach that you could do. Okay. Now, Okay. So that was one method we could do. All right. Now the other thing is that when we started up here, we could approach it a different way. Now, Chris noticed, he says, okay, well, cosine squared is 1 minus sine squared. Okay, that's legit. We can do it. Can somebody see something else I can do? 1 minus cosine squared is sine squared. So because I have this and the negative cosine squared, I could use that identity. Excuse me. So now I could rewrite it as cosine of x plus sine squared of x over sine of x. Oh, well, that was a step I had before, wasn't it? Okay. And the point is that, okay, did it matter which way I started? Nope. I'm going to end up eventually, if you do things correctly, whether you do it the same as somebody else or not, you're going to end up in the same spot. But here we got cosine of x over sine of x. And different things you're going to want to do is that whenever you have, if I have a single fraction, lots of times you're going to end up pulling it apart. Okay, make it two separate fractions. If you have two separate fractions, then lots of times you may end up putting them together to be one fraction, okay, to be able to get them. So this is cotangent of x plus sine of x equals sine of x plus cotangent of x. And it did not matter which way you did it. Both of those processes of getting to the answer are correct. Sweet. Okay. All right, so here's number 4. We want to simplify this expression. Secant of x plus tangent of x times the quantity 1 minus sine of x. And because you could go ahead and multiply first, okay? Or you could, since everything is to first degree, secant first power, tangent first power, okay? Then you're probably going to end up putting everything in sine and cosine eventually, and so it would probably be easiest to do that right away. Now, if the 1 minus sine of x had either tangent or secant in it, then it might be more beneficial to multiply first before you change them. And you can actually do it either way. It just kind of depends on what mood you're in and where you want to go. Because like I said, you can always start different spots. So first I'm going to change everything to sine and cosine. So secant is equal to what? Okay, so we have 1 over cosine. And tangent is sine over cosine. And then we have 1 minus sine x. So here we're just trying to find an expression that is equal to that. Because we're not proving anything, we're just simplifying. So what do I have on the left side here of this, or in the factor on the left side? What do I have? I have a common denominator. So I'm going to put that together. Maybe that'll help me. So we have 1 plus sine of x over cosine of x times 1 minus sine of x. Okay, so can't simplify anything else. I don't have any squares or anything like that. So I'm going to need to multiply. Right? Well, what do I get when I multiply? Now, the right side is over 1, right? Okay. So if I multiply the numerators together, what's 1 plus sine of x times 1 minus sine of x? Well, let's see. If I multiply that out, we get 1. Let's see. I get a negative sign, positive sign, which is 0, right? And then minus sine squared. Okay, so I had the difference of two squares there, right? One plus sign and one minus sign. So I have something squared. Whenever I get something squared, I want to look for a Pythagorean identity. Is 1 minus sine squared of x, is that an identity? Okay, 1 minus sine squared is cosine squared. So this becomes cosine squared over cosine, which just reduces to, or simplifies to, cosine of x. So that whole thing simplified just to cosine of x. Well, that's easy, isn't it? Okay. So here it says the strategy, oops, there we go. The strategies presented above and those to be considered are plans of attack. By themselves are not much help unless you also have some techniques for carrying out these plans. Previous examples of techniques of basic algebra and use of known identities were used to change trigonometric expressions into equivalent expressions. There's another technique that's often useful when dealing with fractions. Okay, and we're going to do number 5 tomorrow, so we're going to go ahead and do number 6. So we're going to prove this one. So here I've given you a plan of attack. Deal with each side separately. Like we just talked about in the example 4, we said, okay, if nothing is squared, I want to change everything to sine and cosine, first of all. Okay. So there's our first thing. Nothing squared, change everything to sine and cosine. So we've got 1 over cosine plus sine over cosine. So we have a common denominator. Now, my second step in my process said, hey, use the same process as example 5. We didn't do example 5, though, did we? Okay, that's all right. Because now, the thing is that we can do things with one side. And reminder, we can multiply by 1, right? If I have a common denominator, or not a common denominator, if I multiply by the same thing, numerator and denominator, I'm just changing the way something looks. I'm not changing its value. Okay, it's kind of like when you get a common denominator, if I multiply by 3 over 3. Okay. Now here's the thing. I have 1 minus sine of x in the denominator here on the right-hand side. Okay. Well, that 1 minus sine of x is half of what? One minus sine of x is half of the difference of two squares, right? So if I was to multiply the numerator and the denominator by 1 plus sine of x, then I would have the difference of two squares there. And when I have once I get that squared term, then I have identities I can work with. And so I'm looking for a squared term to be able to use here. So on the right side now I have cosine of x times 1 plus sine of x. And in the denominator we have 1 minus sine squared. Well, this helps me because 1 minus sine squared is equal to what? Cosine squared. All right? So on the right side, I have cosine of x times 1 plus sine of x over cosine squared. So the most difficult thing about this is, and this tends to be very difficult for people, is the fact that you have to recall all the mathematical knowledge you've acquired, okay, over the years, and you got to put it together and use it. So now on the right side, I can cancel out a cosine. So we have, that cancels. So we have 1 plus sine of x over cosine of x, which is what I had on the left side. Okay? So here's a situation where I wanted to go from the right side to the left side. Now you could have also done this a different way. You could have multiplied the left side here by 1 minus sine of x over 1 minus sine of x. Just that squared term then would have been in the numerator instead of the denominator, and it still would have done the same thing for you. Okay? It's just that we're used to simplifying the denominator. It's kind of like when you have a radical in the denominator or a complex number. Okay? We're multiplying by the conjugate or multiplying by the other part of the difference of two squares to simplify.